Welcome to Lecture 4 of ECE 141. This is part 1 of a series of lectures, well, just 2 parts, but anyway, part 1 of your digital modulation. So I'll introduce to you different types of digital modulation. You've already actually come across one type, and that was your PCM. So remember that your PCM, after you encode your signal into bits, from bits, we can now create a baseband transmission using rectangular pulses. And this is your signaling methods, so your line codes, right? We'll generalize that into passband, basically passband transmissions. So how do we transmit in the passband instead of the baseband? So normally we actually use the passband for transmissions, and we'll see in this lecture. Right? So part 1. So just a review, let's look at our building blocks of channel coding. So from the bits, as you see here, from the bits, we now encode our bits into a form suitable to be transmitted to the channel. And through that, we're going to go through what we call an error correcting encoder, but we'll discuss that in the later part of the course, okay, on a later topic. So we'll focus first on these two blocks right here, the symbol mapper and the pulse shaper. The symbol mapper would map, okay, this is what we have, we map the bits into symbols. And from symbols, we now create pulses. Right? And we'll also defer this for now. Let's just look at the symbols. How do we represent our binary digits or our bits to a symbol? First, what is a symbol? What is a digital symbol? I've been saying that on and on. I have not even given a background. Right. So we represent the bits into digitally modulated signals. So just to refresh your memory, analog modulation, the signals are impressed upon the parameter of a carrier signal. So that means the signal rides on the amplitude of your carrier, or the signal is within the frequency changes in the carrier. Okay? However, that does not apply to bits, actually. How do we represent the abstract bits in reality? Actually, we don't know. You don't know yet. Of course, I know. You don't know yet. So this is what we'll discuss. So we can actually map them to a pulse, and a set of k bits can be mapped to a specific pulse in a set of pulses. The pulses are called symbols. Okay? So from your symbol mapper, let's focus on that. We represent the bits as symbols. So if you have symbols, okay, so different groups of bits create different symbols. Sorry, I forgot to tell you that. Some L bits can be represented as one symbol. The next L bits can be represented as another symbol. So if this is L bits, how many symbols can we make? That's 2 to the L symbols. Okay? Depending on the combination of bits that we'll have. And the different combinations of bits have different symbols. These set of symbols create what we call the constellation. So it's the set of all symbols, and we have a specific group of bits to a specific symbol, and that forms what we call a constellation. So now it depends on the channel what type of constellation you will use. All right. So now let's look at the concept of symbol rate and bit rate. So they're totally different things. Okay. So for L bits, the total number of symbols, as I've said earlier, is m equals 2 to the L. Okay? So that's total number of possible symbols, assuming that we have a symbol source that transmits one symbol every t sub s seconds. So this is your symbol interval. The symbol rate is just the amount of symbols you transmit per second. And if there are L bits per symbol, then your bit rate, or the bits per second, is just equal to the number of bits per symbol multiplied by the symbol rate. Okay, so that's actually very, you think about it, that's just intuitive. You send one symbol per second, then if there's one symbol having 4 bits per symbol, then you just multiply, that's just like dimensional analysis, and you get 4 bits per second. So the value of t sub b here is called the bit interval, and its reciprocal is called the bit rate. Okay? Okay. The average energy per symbol is calculated as, so this is the formula for that. Basically, the probability that the symbol occurs multiplied by the energy of that symbol, okay? And you sum all that, you get the average energy per symbol. Okay? So basically, just average the energies of different symbols. Different symbols could have different energies. So in turn, the average energy per bit is just you divide the average energy per symbol by the number of bits. Okay? The average power by the transmitter is just divide the energy by the bit rate. So the energy per bit divided by the bit rate, the bit interval, is equal to the average power of the transmitter. Okay, so that takes care of the preliminary metrics that of our constellation and our symbols. How do we define them? What is their energy? How much power? Etc. etc. All of these are actually important when you're transmitting. All right. So now let's move to a class of symbols. Okay, this class of symbols form the memoryless symbol mapping. So standard approach is you group L bits and then map them to a symbol in constellation A. Okay? So you map these L bits, okay, unique combination of bits, into different symbols. So if you have a coded bit sequence, for example, and you want to group them into 4 bits per symbol, then you split them into 4. Okay. Split them into 4, and then they have corresponding symbols right here. Okay? Okay. So how do you design this constellation of symbols? Consider your 4-ARI quaternary pulse amplitude modulation transmission. So this is actually just your PCM. Okay? This time, this is how we code the bits. If we have 0, 0, then the signal value is at negative 3 volts. 0, 1 at negative 1 volt, 1, 0 at positive 1 volt, 1, 1 at positive 3 volts. So the series of symbols right here would be encoded as such. And this is actually not different from your PCM. Okay? You're just reversing your PCM. So from bits to signal. Okay? Kind of like that. If you plot it in a constellation diagram, you can see that the signal levels can be mapped into this one-dimensional constellation here. So the distance between two signals is equal to 2D. In this case, D is equal to 1. Alright, in this case, D is equal to 1. So the pulse amplitude modulation works in this format. So if we have an M PAM, so we map the symbols into the amplitude of your pulse, of a given pulse. From the previous example, we use the rectangular pulse. So depending on the amplitude level of the rectangular pulse, we have a symbol. Right? So I've already introduced to you the binary symbol mapping. You just order the symbols according to the order of, or the levels of your mapping, or of your symbols. Gray code mapping, each neighboring symbol only has a 1-bit difference. Right? So, burning question to you, what is the advantage of gray code mapping over natural binary mapping? Gray code mapping actually enables us to easily correct our received signal. So if this has 1-bit error, right? This 1-bit error could be if it becomes 1-1. So basically, they're just neighbors. We can actually see that so by some forward error correction technique, we can actually correct the received 1-1 into 1-0. Okay? And with gray code mapping, we can relate what we call the symbol error rate to your bit error rate. But I'm getting ahead of myself. Okay? So that's the difference between your gray code mapping and your natural binary mapping. Okay, so now let's look at the pulse amplitude modulation. So the amplitude of the symbol defines the bits. Okay? So A sub m here is odd. Alright? A sub m here is A sub m here is odd. And this parameter m is taken from this set. So how do we compute the energy? So we want to know the energy of your pulse amplitude modulation. Well, you just need to get the average energy of your amplitude, A sub m. So A sub m here is random. P squared of t here, since A sub m is constant with time, you can actually factor that out and you'll get this equation right here. That's just the amplitude of the symbol multiplied by the energy of the pulse. So now the average energy per symbol, assuming we have equiprobable symbols, and equiprobable symbols is the most likely scenario, but I'm getting ahead of myself. Alright, so you just accept for now, equiprobable symbols is the most likely scenario. Alright, so the average energy per symbol is equal to just getting the average of all the different amplitudes. Okay? So we have the amplitude defined as this. Substitute that here, okay, and do some math. Okay, so I won't be showing it to you. Basically, it's equal to this. So the average energy per symbol is m squared minus 1 all over 3 times the pulse energy. Example. So we have a quaternary constellation. If we get the average, so there are 4 of them. So that's 1/4. Times the sum of the squares of their amplitude levels. You get 5d squared. For a binary signaling, we have 1/2 if they're equiprobable times the sum of their squares, and you get d squared. Okay. So now we move on to analyzing PAM using signal space. In this case, your pulse P of t is the sole basis for the modulation. Since it only has one basis, then it is in a one-dimensional space. That's why we represent the PAM in a single line. Okay? So these are different numbers or different PAM depending on the number of symbols in that constellation. The orthonormal basis of PAM is just you divide the pulse by its energy. Sorry, by its norm, not its energy. Okay, so the orthonormal basis for that PAM is this signal right there. Okay. So when we're designing a constellation, we need to take note of three different metrics: the energy, reliability, and the rate. The energy depends on the minimum distance between your signals and the total number of points. The energy increases if you increase the distance, the minimum distance between your symbols under fixed number of symbols. If you increase the number of symbols and fix your minimum distance, then you also increase the energy. Generally, if you increase both, then you increase energy. Reliability is measured by the minimum distance. So if there's a minimum distance, there is less chance that your symbol will cross over the boundary and be detected as this symbol. Okay? So if you increase the distance, let's say from here to here, then the probability that this will cross this boundary will be less. Therefore, you have higher reliability. The downside is if you increase this reliability, you actually increase the energy. Sometimes we're limited with how much energy we transmit. Not sometimes, all the time. Okay? Data rate is higher if M is larger. So if M is larger, you can transmit more bits per symbol. And if you have a fixed symbol rate and you increase the number of bits per symbol, you increase your bit rate. What's the downside? The downside is, again, you increase the energy. Okay? Right. Okay, so just to summarize, your PAM signals or series of symbols can be transmitted, creating a baseband digital transmission. Your mth symbol, S sub m, transmitted at time t is equal to mt, is basically this pulse right here, which is equal to some amplitude multiplied by your pulse, time-shifted pulse. And your baseband, digital baseband signal becomes this equation right here. So you have series of pulses with differing amplitudes shifted at different times, forming a train of pulses. Okay? So depending on the pulse or the pulse shape, you can save more bandwidth, you can eliminate what we call inter-symbol interference, etc., etc. However, we'll be deferring that discussion to a later lecture. For now, we have just discussed baseband transmission, but baseband transmission is only possible when you have a fiber optic cable, when you have a wire, you have your Ethernet cable. It won't work when you're trying to transmit wirelessly. And a lot of our devices now use wireless transmission. That is where amplitude shift keying enters. Our pulse will be modulated by a carrier cosine 2 pi fct. So this g of t is what we call the baseband pulse. Okay. So this is a baseband pulse. And since it is modulated by your cosine 2 pi fct, that makes this a band pass or pass band. Okay, so anyway, so this would be your pass band pulse. Alright. So now if we let a PAM signal ride a cosine carrier, your baseband PAM would look like this. So this is your passband PAM, which is ASK, look like this. The dashed line is your PAM signal, and once it is modulated, the amplitude level of your pulse, as you can see here, would vary depending on the signal level. So it's kind of like amplitude modulation, if you think about it. So the symbol is impressed on the amplitude of your carrier. Right? So notice that in this area right here, there's some form of disconnect between the two symbols. Also here, it's not seen as much, but there's a disconnect. And this is actually a bad thing, but we'll get to that later. Okay, so just to compare, the basis for your baseband PAM is equal to the pulse shape divided by the square root of the energy. And you can represent your baseband PAM as this form. The basis for ASK is you get square root of 2 divided by the energy of the baseband pulse multiplied by cosine 2 pi fct. And that makes your your passband pulse, your ASK pulse, have this equation right here. So now we're interested in the average energy per symbol. So your PAM symbol uses your pulse P of t. So with energy EP. So again, this is the average energy per symbol. ASK uses, again, some pulse G of t baseband multiplied by the carrier cosine 2 pi fct. The corresponding average energy per symbol becomes this. So because of the cosine, the energy of this G of t would be halved. Okay, resulting into this average energy per symbol. That means your ASK uses twice the energy just to maintain the average energy per symbol. So that's the downside of transmitting over a passband. Okay? So your passband actually consumes more energy than your baseband. And actually, that's a given. So now what does the constellation look like? So the minimum distance between signals, or two symbols, using signal space analysis, for PAM, that's 2 times the square root of E sub P. That's the energy per pulse. For ASK, it's actually the square root of 2 times the energy of the pulse G. Okay? So basically, we're just going to reiterate. If we use the same baseband pulse, we need twice the energy just to maintain the same symbol distance. We need twice the energy just to maintain the same symbol distance. And that's really a downside of your ASK as compared to PAM. Okay. So aside from amplitude, what parameter can we vary and impress our symbol on? We can actually impress it on the phase. So we have your phase shift keying. So instead of shifting our amplitudes, we shift our phase depending on the symbol transmitted. Okay, so that would mean our carrier would now have a phase shift theta sub m depending on the symbol. And the phase shift is now this formula right here. So it's from 0 to 2 pi at increments of m minus 1 over m. Okay? And your m is still 1 to m. So if we expand this expression for your symbol, okay, we get this expression right here. And recall that this cosine theta and this sine theta form an orthogonal basis for your constellation. That means PSK is a two-dimensional constellation. This is something that you won't be able to find in your baseband signal. So you won't be able to find this in your baseband signal, mainly because your cosine and sine are inherently orthogonal. You won't find this in a baseband signal. So the baseband signal is just a rectangle. How are you able to find an orthogonal signal with a rectangular pulse? So now we have PSK having two-dimensional constellation. That means PSK constellation looks like this. Okay? So this is a 4 PSK. So it's on the four corners on different parts of a circle. 8 PSK looks like this, so on and so forth. The good thing about PSK is that it has a constant amplitude. That means it has a constant energy per symbol. Okay? It's a constant amplitude, it has constant energy per symbol, and you get this nice energy per symbol expression right here. It's just 1/2 the energy of the pulse. So if we solve it using signal space, the orthonormal basis for PSK is these two expressions right here. And now we can rewrite our PSK signal in terms of the orthonormal basis. We can see that your symbol M can be defined by these two components right here. So now it becomes this one. So two consecutive symbols, we need to solve the minimum distance between them. Just get the norm of their difference. And you'll get this expression right here. This expression inside can be rewritten as this using your half angle formula. And from your half angle formula, well, if we have M, large M, so if M is sufficiently large, maybe around 8, so we can actually assume or approximate this sine pi over M to become approximately pi over M. And we have this simple expression for the minimum distance between two symbols. Right? This is your PSK. Now you have your ASK and your PSK. We can actually combine them to form greater number of constellations. Right? So here we have a constellation with 8 elements, 2 different amplitudes, and 4 different phases. Here we have a constellation of 16 elements, and you have 4 different amplitudes and 4 different phases. Okay? So this is an example of combining ASK and PSK. So this will actually lead to a higher class or a higher level of constellation generation, constellation design, but we'll end the lecture here. So if you have any questions, so don't hesitate to leave a comment in the comment section below. I will answer it as soon as possible. Okay? So thank you for listening. I'll see you next meeting.